In our previous video lesson, that was topic 1.2a, nuclear model and stability, we talked about the characteristics of the nucleus, how the forces play out, and how the short range of the strong nuclear force contributes to the stability or otherwise of any nucleus or any atomic element. Now, we said that the strong nuclear force has a very short range, and as a consequence, when the nucleon number increases, the radius increases, and the range of the force starts to diminish, and therefore energy is released from the nucleus in the form of particles or radioactive particles. So what we're going to do today is have a look at how this principle can actually contribute to the energy released in nuclear reactions, particularly fission and fusion. So let's quickly review some of the ideas associated with our last video lesson. So here are our nucleons, here's our nucleus, and we know that the sum of the strong nuclear forces, the attractive forces that is, must be greater than the repulsive forces, which are the electromagnetic forces, in order for the nucleus to be stable. The abbreviation we're going to use for electromagnetic force is EMF. Now, since we're going to be calculating energy, and we know that the fundamental unit for energy is the joule, we also know that the force at play here, or the sum of the forces, is required for work to be done to either bring nucleons together or to split them, or to split nuclei. And that force obviously is the sum of the strong nuclear and electromagnetic forces, and the distance relates to how close they are, the range of the strong force, etc. And the unit, of course, is the Newton meter. So 1 joule equals 1 Newton meter. Now, factor conversions for converting, let's say, from joules to Newton meters, or from Newton meters to joules, is 1 joule per Newton meter, or 1 Newton meter per joule. Now, we know that the distances are very short, and since the distances are very short, the forces must be very, very great. When we're talking in terms of, the relative distances, because we know that the distances associated with the gravitational force are actually quite large by comparison. But when we say very short, we know that they fall within this range of the nucleus, or the strong nuclear force acts at distances less than that, and therefore there is a lot of potential energy in the nucleus. Now, this potential energy is also very large, because if the force is going to be large, the distance is short, the energy release is also going to be very large. So now we can apply Einstein's famous equation in order to determine the magnitude of the energy released when a nucleus is split, or when nucleons are brought together to produce new elements. The learning goals that we will cover in this lesson, as you can see there are 11 of them. We'll probably break up this lesson into 2 parts, and in this first part we'll cover learning goals 1 to 4, and in the second lesson we'll cover specifically those learning goals that relate to fission and fusion. That's learning goals 5 to 11. So some of the terms that you need to look for as we go through this: mass defect, binding energy, and binding energy per nucleon. So binding energy is the application of Einstein's equation, E equals mc squared. Binding energy per nucleon refers to the amount of energy required to bind one nucleon at a time to the nucleus. Next, describe the energy in electron volts and joules. Now, in nuclear physics, we're going to use the electron volt because we're working with very small numbers. We can always convert that to joules. The mass-energy equivalence relationship simply means that mass can be converted to energy and energy can be converted to mass. Solve problems involving Einstein's mass-energy equivalence relationship, and that's as far as we'll get in this lesson. So we're going to use this model to try and explain the binding energy and the strong nuclear force holding the nucleus together. So here is our nucleus, and what we're trying to do is we're trying to pull away one nucleon at a time, whether it's a proton and a neutron. We're trying to pull it away and to put it on a table so that these particles now experience no strong force, so they're not bound in a nucleus but are separated nucleons. Now, the energy required to remove a nucleon is the work done, which is Fd. So force times the distance moved, the distance we separate the nucleons from the nucleus itself. The work needed is force times distance. We need to apply force and we need to move it through a particular distance. Now, this distance might be a small distance because as far as we understand the limits of the strong nuclear force, the energy just simply needs to overcome that range. Once that range has been overcome, the nucleons will be completely separated. Now, if we consider the mass of the nucleus and compare that mass with the mass of the nucleons, something very interesting happens, something unexpected happens. What we find is the separated nucleons, so when these nucleons are separated, the mass of the nucleus is actually smaller than the mass of the nucleon. So it's like when we separate these nucleons, their mass increases. Now, that's very strange, but experiments have verified this to be true. So we're going to apply some of those ideas now in order to think about how much energy is released when this breakdown of the nucleus occurs. We call this mass difference, we call it the mass defect, and it's the value that's represented in the equation E equals mc squared. What we're looking at here is a nucleus and this binding energy. How much energy do we actually need to separate the nucleons? So we call this the binding energy. In other words, the sum of the energy that binds all these nucleons together so that we separate them. And once we do that, as we saw in the previous slide, the nucleus, when the nucleons are bound together, has a smaller mass than nucleons when they're separated. Now, in order to make this calculation, here is our delta M representing our mass deficit. And the mass of the proton, Z, is the proton number. Now, I did call it deficit, mass defect or deficit, either is okay. A is the nucleon number, and mass of the proton, mass of the neutron, minus the mass of the nucleus. Now, when we subtract the mass of the nucleons from the nucleus, we find that the number is greater, or the mass is greater. Let's define binding energy now, so we have a clear understanding of what it actually is, because it can be used in a few different contexts. But the binding energy is equal to the amount of energy released in forming the nucleus and is given by this equation, which really is a variation of E equals mc squared. There's your change in energy that occurs between the nucleons being in a nucleus and then being separate. This represents the mass defect, and of course multiplied by c squared. So delta E, we can think about it as the binding energy, and of course c is the speed of light squared, which is 300 million meters per second. So let's have a look at a practical application of this binding energy formula, or the version of E equals mc squared, that we can apply to starting to work with nuclear reactions. So what we have here is we've got a isotope of helium which has a mass of 6.6447 by 10 to the negative 27 kilograms, and we're asked to find the mass defect, and from that value determine the binding energy. So we're given the mass of a proton in kilograms and of a neutron in kilograms, and we know that in order to find the mass difference, we have to consider the number of nucleons in the nucleus and of course the number of protons. So to find delta M, we've got 2 protons, and 4 minus 2, we've got 2 neutrons. And of course we take the mass of the nucleus where the nucleons are bound from the mass of the nucleons when they're not bound to the nucleus. So let's put the values in, and as we do the calculations, beware or be careful that these 6 decimal places can sometimes be a little bit tricky to work with, and if we add that together, we come out with a mass defect, delta M being the mass defect, 5.0398 by 10 to the minus 29 kilograms. So that is the change in the mass between when the actual nucleons are separate, that is not in the nucleus, and when they are bound in the nucleus by the strong nuclear force. Now, to convert that mass to binding energy, we simply use a variation of Einstein's equation, delta E equals delta mc squared, delta M being the mass defect, and of course the speed of light is 3 by 10 to the 8 meters per second, and we get this value here, which is the binding energy. So what that actually means is that if we take these nucleons and we do work, we use energy to combine them, get them close enough so the strong nuclear force kicks in and binds them, we need this much energy, hence the term binding energy. Here is another similar problem, but this time instead of using kilograms, we're going to use the more common unit for nuclear calculations, that is the atomic mass unit U. So this time we're told that the mass of the helium nucleus is 4.0026 atomic mass units. For hydrogen, or the proton, it's 1.0078 atomic mass units, and instead of using kilograms, we're going to use atomic mass units to determine the binding energy. Now, the same principle applies. We want to find this binding energy. Here we've got the reactant, if you like. If we represent this as a nuclear reaction, we think about the mass of the products, and we subtract the mass of the reactants from that. So to find the mass difference, there's the total mass of your nucleons outside the nucleus. Here's your mass of your helium nucleus with the nucleons bound together, and you can see the numbers are a lot easier to work with, such that we get a mass difference of 0.0304 atomic mass units. Now, instead of applying the values into this equation and using the speed of light each time, what we're going to do is we're going to say, well, what is the energy released if we're going to convert one atomic mass unit of mass into pure energy without using c squared. Now, if we were to use c squared and do all our conversions and apply it to this equation, we'd get one atomic mass unit would be equivalent to 931.5 million or mega electron volts. Now, we'll talk more about the electron volt down the track. We need to have some understanding of the electrical nature of energy, but we'll talk about that later. But at this point, all you need to know is that one atomic mass units is equivalent to this much energy based on this equation. So when we do our calculation, we use our conversion factors. So 1U per 931.5 mega electron volts if we're converting from mega electron volts to atomic mass units, or in this case we're converting from atomic mass units to mega electron volts. So we'll apply this conversion factor and it gives us a nice even number of 28.3 mega electron volts. That means that every time this helium nucleus is split such that the protons and neutrons are not bound by the nucleus or the nuclear forces, this is the amount of energy that's required to achieve that. Now, we can convert this to electron volts using our conversion factor for mega meaning 10 to the 6. So we can simply convert that to electron volts. That would give us 2.83 by 10 to the 7 electron volts. Or if we want to convert it to joules, then there is another conversion factor that we can use, and this is a conversion factor you will be using regularly down the track, where what we do is we multiply our electron volt values by the conversion factor for joules to electron volts, electron volts to joules, and multiplying this out, it gives us 4.5 by 10 to the minus 12 joules. So that's how you can convert from mega electron volts to electron volts and then to joules, or obviously you can go the other way.